means. So, like I said, factoring is kind of the opposite of multiplying. It's kind of like dividing. We don't technically like show our division completely. I mean, I will a little bit as I show my work. But so when you think of factoring, it's really like you're dividing something out. So I'm going to write that here. So the warm-up question is going to kind of get us thinking about this. And so what we're going to do today is we're going to basically, this warm-up is distributing in. We're going to take out now today. So we're going to do the opposite of that today as we're working. So in this problem, we're going to distribute these in. You guys have done this before. So you want to take a minute to do that. Same thing with the 6y. Remember our multiplication rules here. So here we're multiplying. So I have 5a to the second times 4a to the second. So 5 times 4 is 20. And a to the second, when we're multiplying, this will become a to the fourth. Then 5a to the second times 2a. So it's a positive 5 times 2 is 10. And then that's going to be a to the third. 2 and 1. And then 5a to the second times a negative 7 is going to be a negative 35 a to the second. And that's a simplified else's like terms. Same thing happens on the second one. We're distributing n. So 6y times 4y to the second. So that's going to be 24y to the third, the 1 and 2. Minus 6 times a negative 1, so a negative 6y to the second. And then 6y times a negative 5 is a negative 30y. And then again, that's as far as we can take that. Guys, off your phones, please. So what we're going to do today is we're going to do the opposite of this. So we're going to take this and make it look like that. Kind of strange. So we're going to go backwards with this. So it's going to look like this, and then we're going to make it look like that. So we're going to kind of undo this. So these two are, like I said, these two are definitely like kind of leading us into what we're doing today, where we're going to do the opposite of that. And it may sound harder than it is, but it's just dividing instead of multiplying. So for our greatest common factor here, actually I might grab my phone as a cheat sheet. I just want to make sure I have all the bullets.
No phones in school.
No phones at all. Sometimes when I have bullet points, I forget what I meant to put there, so I want to make sure I don't have my note sheet as a guide.
Why don't you have your note sheet?
I didn't have it printed for some reason. I don't know. I know.
But you were programmed.
Mess. Maybe I don't have it. Oh well. It's okay. So, what a greatest common factor is called a GCF. So, you guys have actually learned about greatest common factors before when you learned fractions. And again, obviously fractions wasn't everyone's favorite thing in the world. But a greatest common factor is basically what you would divide out of a fraction. So like if I was talking about like 18 over 12, I would divide those both by 6. So 6 would be my greatest common factor. So that's called the GCF. So we're kind of looking for that GCF of all our terms. So when we do this, we're going to find the largest number that can divide into all the the values in all the terms. Bless you. It's the largest number that can divide into all terms. So in this case, between the 18 and 12 would be a 6. Now, we won't be using fractions, but that kind of gets you thinking about it. But then we're also going to find the greatest common factor among the variables. So if I'm looking for the greatest common factor, and I'll use like x to the 5th and x to the 3rd, what do those two have in common? What do both of them have to give? X's. How many of them can they both give? Not total, but each of them. They can each give 3. So it'd be like saying, hey, let's all chip in and buy breakfast or let's buy, I don't know, donuts or something. And I said, everyone's got to give the same amount. So I can't say, I'm going to make you guys all give me $2 if you don't have $2 to give. So we have to find the value that both of them can give. So both of these can give an x to the 3rd. So it's the largest exponent that both have in common. So the GCF in this case would be an x to the 3rd. Because it's what they all have in common. They can all give an x to the 3rd. Obviously this guy has more, but he can't give, it's not even, or it's not fair if I expect people to give different amounts. So what we're going to do for this factoring, and this is going to feel weird at first, we have to get used to it, it's something new, it's not probably something you've seen before, or if you have, maybe you won't remember it as well. So what we're factoring is we're going to find the GCF, so the greatest common factor. So I'll use those words GCF, and I'll put it on the outside of the parentheses. So the GCF is going to go on the outside. And so we're going to find the GCF of all terms, and then we're going to put that on the outside of the parentheses. And I'll just use parentheses like the symbol there. Once we've done that, then we're going to basically divide everything by that GCF. We're going to divide all the terms by the GCF, and inside the parentheses we're basically going to write the leftovers. And I'll explain what that means. Oh, I just had to go back inside. So the leftovers after division are going to go inside here. I'll show you guys like what I mean with actual numbers, but kind of having the directions here hopefully will help. So they want us to use this distributive property to factor these two terms. There's only two terms this time to worry about. So we have to find the GCF of both terms in this case. I'd say all terms, but there's only two. So we have to find the common number that goes into both, so the common like coefficient. So between 15 and 25, what number can divide into both of those? What do you think? Yep. What's it? 5, yep. Does anyone think anything different? 5 goes into it. We want to find the biggest one, and 5 is it. So 5 divides into each of those. So 5 is my GCF of those two. And you won't have to write it out this way every time. I'm just trying to get you guys thinking about it. How about between the x squared and the x? What's common? A single x. The reason why it's only a single x is because this one only has a single x to give. This one has 2, but again, I can't take more from one of them. So like I can't say, well, you give 2 and then you give 1, that's fair. That's not. So the GCF in this case would be an x. So that's what we're going to put on the outside of the parentheses. So I have to write the 5x out here. So then I'm going to kind of leave parentheses kind of as a blank there. So this is our GCF. So we found that from like talking through that. But now I have to divide all the terms by the GCF. So I'm going to take these terms and divide this out of them. Because again, this is the opposite of multiplying. So rather than multiplying in, we're dividing out. So we're going to take 15x squared and divide by 5x. And we just did this last chapter, so this should be something you should be able to do. So 15 divided by 5 would be 3. X squared divided by x, just an x. So 3x. I'm going to bring that minus along. 25 divided by 5 is 5. And then the x's will just cancel. So this is considered the factored version of this. Now, if you're ever unsure, if you're like, what did we just do there? Did I do that correct? This is what they're asking you to do. But if you want to check your work, you could multiply back in and check and see that it actually like does multiply to be that value. Like it should be that if you multiply that back through. So these two are equivalent statements. They mean the same thing. And it probably seems kind of weird right now, like it doesn't seem necessary, but we end up using this for a lot of things in math. Like my algebra 2 students will use this a ton, and they'll use it to solve problems and like work through other things, graphing, and all sorts of different things this is used for. So it doesn't seem super helpful right now, but it's something we have to learn how to do. So let's flip the page. We'll do a couple more and then do some practice. Okay, so this next one. So again, between these two terms, there's only two terms to worry about. We want to find the number that's common. So what number can be divided into both? 2, right? So 2 can divide into 14, 2 can divide into 2. So we're going to put a 2 on the outside. So again, like I said last time, I said you don't have to do all that extra writing if you don't need to. How many C's are common? How many C's are common here? What do you think? How many C's can we take out? Just 1, because this is a C to the first, that's a C to the second, so I can only take out 1. So I'm going to take out a 2C. That's going to be my GCF. Now, I like to show this as dividing. You don't have to show that, but it's like visually what's happening. Dividing that out, so 14C divided by 2C. 14 divided by 2 is 7. The C's will cancel. The 2's will actually cancel or become 1. And then c squared over c is just going to be there's more c's on top, so c to the first, right? Or just c. Let's go down to number 7 if we could. So we can go down to number 7. What? Is not a nice one? Oh, that one's really bad. Why am I mentioning that one? So let's talk about 7 real quick. Are there any numbers common? No, 7 and 9 don't have a GCF. So there's no numbers common. How about the variables? There's 2 of them, but they're not the same variables, so they're not common. It'd be like one of you guys having like money from another country. Like that wouldn't be like work for us. Yep.
Oh, no, wait, never mind, I just got contradicted.
No, it's okay. So we just say there's no GCF here. You can't factor it. So it's totally possible to have it not be factorable. So don't think it's always going to be factored. Most of the time, the ones we'll get in our homework today are probably going to be able to be factored, but don't think all the time they will. All right, why don't we actually grab whiteboards and practice this a little bit before we make them a little bit tougher? What's that?
It's like,